In number 53, we have an amusement park ride. It's one of those big swings, and it consists of a 365 uniform arm, 10 meters long, with two seats of negligible mass connected to the lower end of the arm. How far from the upper end is the center of mass of the arm? Well, that one's pretty easy. If this is a uniform arm, the center of mass is going to be right in the middle here. And that's going to be 5 meters down from the top of it. So for part A, pretty straightforward, just 5 meters. Okay. The gravitational potential arm is the same as if all the mass were concentrated at the center of mass. If the arm is raised for a 45-degree angle, find the gravitational potential energy where the zero level is taken to be 10 meters below the axes. So in other words, we're setting h equals 0 right here at this level here. All right, not so bad. Got to do a little bit of trig though real quick. So here it is at 45 degrees. And the question is then, how far above the bottom is this point? Just doing a little bit of trig, we know that's 5 meters from the top. And if we draw a line straight across there and just doing a little bit of trig, 5 times the cosine of 45 degrees gives us 3.54 meters, which means it's going to be 6.46 meters above the bottom, the sum of those two being 10. So plugging in, figuring out gravitational potential energy, mgh, mass of the arm, 365, times gravity, I'm calling 10, times 6.46 meters gives us a gravitational potential energy at that point of 23,600 joules. C, the arm drops from the position described in that. Find the gravitational potential energy when it reaches vertical orientation. Well, vertical orientation, the center of mass is now back to this point right here. And so that's going to be 5 meters above the bottom. Plugging in our numbers, again using 10 for gravity, and height is 5. Its gravitational potential energy there is going to be this. So again, just talking about we're going to end up in this case figuring out the change in gravitational. We'll use that part D. Find the speed of the seats at the bottom. All right, so what's happening in this case? We're converting the change in gravitational potential energy into rotational kinetic energy. And you might say, well, wait, we're looking for speed. Isn't that regular kinetic energy? Yeah, but in this case, this beam doesn't have kinetic energy. It's actually pivoting around one end. So it's just rotating around one end, and the type of energy involved in this case is just rotational kinetic energy. So in this case, just using energy initial plus work equals final energy, it's going to start with some initial gravitational potential energy. There's no energy loss or gain in the system, so no work. And the final energy is going to be the final gravitational potential energy that we just calculated, along with the rotational kinetic energy. We know the numbers for the original gravitational, that's right over here. And we know the final, that's this number right here. And then remember, rotational kinetic energy, instead of being 1/2 mv squared, is 1/2 I omega squared. And in this case, a rod pivoted around one end has a rotational inertia I of 1/3 ml squared. This is back from your table again, so you can easily look it up. But just plugging in then the mass and the length. In this case, mass again 365, length is 10. It's not just the distance from the center of mass to the point, it's actually the whole thing. And if we solve this, by the way, just quick on this note, from this step to this step, I subtracted 18,300 from both sides, and I still kept 3 sig fig, so back down to this. And then solving this, we can solve for omega. Omega of the entire arm is going to be 0.397 radians per second. Part D, though, actually asks for the speed of the seats at the bottom of the swing. So I don't think they were looking for angular velocity. They actually wanted regular velocity. How do we convert that? Well, the swings are at the end of this thing, so at a distance of 10 meters away from the pivot point. And if you remember, velocity is equal to omega r, where in this case r is going to be 10. Without even using a calculator, it's just going to move our decimal place over a little bit. So 3.97 meters per second should be the velocity of the swings at the bottom of the swing. Hope this helped.